Analytical tools. Maps often require more than a visualization of spatial data for users to answer questions and solve problems. The right data might be on the map, but analytical methods offer the best answers or solutions to a problem. There are many analytical tools in GIS. Let's take a look at a few of these. Analysis tools. I'd like to give you a flavor of just a few of the analysis tools that are found in GIS. Let's start with proximity analysis. In this case, this proximity analysis is using buffers. A buffer in GIS is an area that's defined by the bounding region determined by a set of points, lines, or polygons, and they're set at a distance that you define. So in this example, this was a project that I had worked on a few years ago with trauma physicians in the emergency department at Children's Hospital of Pittsburgh. We had a data set of about 90-some injuries in Pittsburgh, and these were severe injuries of kids under the age of 14. And we knew where these were happening, and they were happening near the residence of the children. So the yellow dots that you're seeing here are where the approximate location of those injuries occurred. Then we decided to do a study looking at the proximity to parks. So one of the questions we had was, if a kid lives closer to a park, are they more or less likely to be injured? So we set up two distances. So we set up a distance of 0 to 600 feet and 600 to 1200 feet of the park. Now, the buffers that we created here are what we call as the crowfly buffers. These do not actually take into account the street network below. But it was a good proximity to say, okay, this is about how far a kid would live from a park. And one of the interesting findings that we did see was that, in fact, kids were more injured the further away they lived from a park. And this was just the start of the project. We later explored things like poverty indicators and other physical characteristics that might lead to the fact that we have more or fewer injuries within the proximity of parks. Buffers for proximity analysis. A buffer is a polygon surrounding a map feature of a feature class. As an analyst, you would specify a buffer's radius, and then the buffer tool would sweep the radius around each feature, remaining perpendicular to features to create buffers. For points, buffers are circles. For lines, they're rectangles with rounded endpoints. And for polygons, they're enlarged polygons with rounded vertices. Generally, you would use buffers to find out what's near or approximate to features being buffered. In this scenario, doctors and researchers at a pediatric hospital in Pittsburgh wanted to explore possibilities for a prevention program to reduce youth pedestrian injuries from cars. And they had two hypotheses. One was that poverty contributes to youth pedestrian injuries because of congested and low-quality public spaces for play, resulting in kids playing in or near streets. Also, poverty leads to a tendency for low parent guardianship, especially in female-headed households. A second hypothesis was that proximity to parks reduces child pedestrian injuries because play areas in parks tend to be away from vehicle traffic. And adults accompanying kids to parks often have supervision and can prevent accidents. So contrary to the second hypothesis is the possibility of increased risks of pedestrian injuries with children walking to and from parks, but the researchers believed that this was not an effect and that the lowered risk of injuries would be if kids lived near parks. So in this example, the primary data set that was used was from the emergency department at the local hospital. And the data set was severe pedestrian injuries of kids under the age of 14 over a 5-year period. So it had a lot of limitations because it was a very small data set. But nevertheless, it was a good way to illustrate how GIS could be used to begin to analyze whether or not kids who lived closer or farther away from parks were more injured. The buffers that we see here are in two distances around parks. The first is a 0 to 600 foot buffer, and then a 601 to 1200 foot buffer. That's overlaid then with the locations of the injuries of the residences of the kids, and those are the yellow dots that you see here. So by having these two layers, you could spatially join the layers together and then count how many injuries were within each buffer. Further explanation or exploration that wasn't shown here was overlaying this with how many kids actually live within those buffers. So those would be looking at something like an injury rate. So the data set here could be just looking at the number of injuries within each one of the buffers or the rate of injuries based on the number of injuries and then also the number of kids. So when added with the number of youths per 10,000, we found that there were actually 45% higher injuries in the 600 to 1200 foot buffer ring than in the 0 to 600 foot buffer ring. And the conclusion was that the youths that live closer to the buffers are playing in the parks, which tend to be the safer environments, and being removed from vehicular traffic. In this scenario, doctors and researchers at a pediatric hospital in Pittsburgh wanted to explore the possibilities for a prevention program to reduce youth pedestrian injuries from cars. And they had two hypotheses. One was that poverty contributes to youth pedestrian injuries because of congested and low-quality public spaces for play, resulting in children playing in or near streets. Poverty also leads to a tendency for low parental guardianship, especially in female-headed households. But the second hypothesis that used buffers was that proximity to parks reduces child pedestrian injuries because play areas around parks tend to be away from vehicle traffic, and adults often accompanying children to parks and their supervision could prevent accidents. Contrary to the second hypothesis is the possibility of increased risks of pedestrian injuries to children walking to and from parks, but researchers believe that the net effect is lowered risk of injury for kids living near parks. The primary data set that was used in the study was a collection of 94 cases of severe pedestrian injuries of kids under the age of 14, drawn from a recent 5-year period. So of course the data has limitations. Among them is that the sample size of 94 is too few cases to draw any strong conclusions. So as an example, Pittsburgh has 90 neighborhoods, so the average is slightly less than 1 injury per neighborhood. But it was good enough to start to look at not only the effect of these injuries per neighborhood, but then also near the proximity of parks. One other assumption of the data set here was that the location of the injuries were also the locations of the residents where the kids lived. And that's not always the case, but that was the data that we had. The buffers that are used here were in 0 to 600 feet buffers from the proximity of the edge of the park, and 600 to 1200 foot buffers beyond that. So in GIS, you could take the proximity buffers and then spatially join those with the locations of the injuries to just get a general count of the number of injuries that are in the proximity of the first buffer and the second buffer. But another thing that was done in this project was added the number of kids who live within each one of those proximity buffers to get the rate of injury. So the rate of injury per 10,000 youths found that there was a 45% higher injury rate in the second buffer, the 600 to 1200 foot buffer, compared to the 0 to 600 foot buffer. So that supports the hypothesis that living near parks reduces youth pedestrian injuries. Network analysis as an analytical tool uses a spatial data type, a network data set, which is used for estimating travel distance or time on a street network. So similar to how Google Maps might tell you how long or how far it will take from you to get from point A to point B, a network analyst within GIS also allows you to show time and distance. Networking tools allow you to create service areas that are similar to buffers, but they're based on travel over a network. And usually a network is a street network data set. So if a point, say for a retail store, has a 5-minute service area constructed using network analyst tools, then anyone residing in the service area has at most a 5-minute trip to the store. In this example, the Pittsburgh Public Works Department was considering swimming pools to close due to a financial crisis that the city was facing. But they wanted to know which pool they should close based on the number of youth that were living near each one of the swimming pools, and also the number of youth who had a pool tag, which would gain admission to each one of the swimming pools. So instead of just creating a buffer around each one of the swimming pools that would create what we call as a crowfly buffer, they used the network analyst tool to say how long would it take for each one of these youth to get to each swimming pool. So what we're looking at here is a service area with travel times to each one of the swimming pools. And the cutoff numbers that we're looking at here are the number of minutes. So you can see that a travel time of 1 minute or less is excellent. 1 to 2 minutes would be very good. 2 to 3 minutes is good. 3 to 5 minutes is fair. And 5 minutes and higher is slightly poorer. So you can see that each one of these buffers here is from each swimming pool and showing the time that it would take to get to each pool. And the further project here looked at then joining each one of those buffers with the number of youth and the number of youth with pool tags. Data mining as an advanced GIS analytical tool is exploration to find hidden structure in large and complex data sets that has some interest or value. Multivariate data clustering, as shown here, is a branch of data mining that finds clusters of data points that are close to each other but distant from points of other clusters. The data shown in this example is serious violent crimes from summer in Pittsburgh with the data mapped as points. The crimes are then ranked by the severity using FBI hierarchy numbers. So, for instance, 1 is the most severe crime would be murder, and 4 would be the least severe crime, aggravated assaults. In addition to the severity of crimes, you could then add other data to cluster, things like race, age, or gender of the arrested persons. So the end result that we're looking at here are the clustering of these types of crimes, and then we have that overlaid with 2 other layers, a poverty risk contour that was actually created originally from spatial analysis, and then also the police zones in Pittsburgh. Data clustering like this is purely an exploratory method. There are no right or wrong clusters, only more or less informative ones. An example of an advanced spatial analysis tool is kernel density smoothing, or KDS. KDS is a widely used method in statistics for smoothing data spatially. The input is typically a vector point layer, often the centroids of polygons for population data, or point locations of individual demands for goods or services. And KDS distributes the attribute of interest of each point continuously and spatially, turning it into a density or heat map. So in this example, we're looking at 2 things: a combination of a model that would take each one of these point features with different variables to create a poverty index. And so the example that I have here on the right, though, is looking at an example from the food bank, the Greater Food Bank of Pittsburgh. And they had a question on whether or not their locations of where they distributed food were in locations of where we had people in poverty. So what you could do here is create a kernel density map made of multiple variables. And in fact, the variables that they used in this map were 8 different poverty variables that they defined for people in need of food. They combined them together into a model to create one kernel density heat map showing the high-risk areas. So you see that the low-risk areas are in green, medium risk are in shades of yellow to orange, and then the high-risk areas are in shades of red, overlaid with the location of the community food members. And another thing you could do, there's a lot of things you can do with kernel density mapping and these types of maps. You could also then take that data and create contours around the hotspot areas and then create vectors of those, and then maybe count how many people you have in those areas, or you could look at actual places of possible distribution of food in those areas, or just to see if the areas of distribution are in fact in the areas where you have high poverty. There are many recent advances in 3D analysis for GIS, leading to innovations in architecture, engineering, construction, urban design, and planning, just to name a few. The image that you see here on the left is using LiDAR data, which is 3D point data that was collected in the city of Pittsburgh and then used to build 3D models of the buildings in Pittsburgh. You also see that there are innovations in how to do this. We have a spin-off company called Carta that is using very inexpensive tools to allow you to very quickly capture 3D data from buildings or even things like construction sites. So the image that you're looking at here in the upper right-hand corner is an image of our Tepper quadrangle that was recently built on Carnegie Mellon's campus, and this was during construction. And these devices could be also attached to things like drones, or they could be used underground. And in fact, they don't need global positioning systems. So you can use these in any situation, both interior and exterior. Because GIS has data attached to each of its features, you can do advanced analysis of quantifiable data using tools like CityEngine and procedural rules. CityEngine is Esri's advanced 3D modeling software for creating huge, interactive, and immersive urban environments. Because you can create a massive city all at once using modeling techniques such as procedural rules, you could do things like identify the height of a building or the number of stories a building has, and what is the general look of the building, what kind of material is being used for the building or the roofs. So this allows you to create these architectural styles and features that allow you to create different design scenarios from two-dimensional models brought into 3D. The 3D models also allow you to show plan changes and alternative designs. So you can, again, this is different from something like Google Earth, which allows you to visualize your models, but not necessarily quantify the data. Esri's software such as ArcGIS Pro 3D and CityEngine, combined with other gaming technologies such as Unity or Unreal, allow you to really bring your 3D scenarios to life. So for instance, you could create an augmented or virtual reality tour of an area. The image that you see here on the left is a project that I recently worked on with the City of Pittsburgh City Planning Department and our Master of Urban Design students at Carnegie Mellon to look at different scenarios for a streetscape. You could then advance that and take these models into tools like Unity or Unreal to look at virtual reality. You could transport yourself to a different part of the city, or you could dynamically change information about the city. So this is an area that is just at its infancy, but really starting to explode with a combination of integrating things like BIM models, building information models from a developer, or other information from architects, combined with these advanced technologies and tools to really create an interactive, interesting model of a city. There are also 3D tools that allow you to easily share your 3D data. The image on the left is a research project by one of our PhD students at Carnegie Mellon who looked at energy simulation data. So she looked at energy consumption data per building, and she also attached that with building material information, and then showed the consumption at a neighborhood level. So she combined this with something called a web scene and a story map in order to be able to describe the information in her project and then share it interactively online as a 3D model. The image on the right is an example of a web scene. This is something else you could create from CityEngine or ArcGIS Pro. And in this case, you can look at different development scenarios, you can turn layers on and off, and you can also ask for public input about the different information that you see in your web scene. So both of these are very interesting interactive ways to share your 3D data.